This is our condensed notes for honors geometry, chapter 2. To begin with, let's talk about inductive reasoning. This is reasoning based off of patterns and examples. So numerically speaking, we have 4 different examples here. I would go ahead and pause the video and see if you can figure out the numbers that go in these different blanks. And when you're ready, you can go ahead and return the video. I'm assuming that you've had a chance to work on them. The first one is going to be a positive 7, negative 8, positive 9. The numbers are alternating between positive and negative, and the absolute values are increasing by a value of 1. The next one has 2 patterns going on. There's a pattern of zeros followed by multiples of 7. The third one gets to be a little more difficult, and for this one, I could look at the differences here and see these keep going up by 2 greater than before. And if I even want to go to a second row of differences, I could see that those are increasing by 2 to make it even more obvious. 26 plus 11 means 37. Add 2, 37 plus 13 is 50. And I know I need to add 15 to get up to 64. I said, could you figure out not the first term, the second term, or the third term, but could you figure out the nth term? Do you figure out what the formula is? Do these numbers look like a specific pattern, the way that we could describe the other numbers? I'll tell you, it is a specific pattern. The numbers 1, 5, 10, 17, and so forth might not look like they're common, but if we subtract 1 from all of them, we can see that these numbers that I'm writing are significant numbers. In fact, let's put 64, that should be 65. Oops, got that one. All these numbers are 1 more than a perfect square. So our first term is 1 squared plus 1. Our second term is 2 squared plus 1. So this would be n squared plus 1. Kind of an interesting pattern. And the fourth one might even be harder for you to notice, because if you look at the first row of differences, these numbers don't seem like they're very significant. But if I look at the difference between these, 7 to 19, that's 12. 37 to 19 is 18. 61 minus 37 is 24. So in the second row of differences, while the numbers aren't the same, I do start to recognize what's going on. And then to emphasize, I could look at the difference between those. And these all change by 6. So there would be a 30 in the second row. 61 plus 30 is 91. Add 91 onto 126. And it looks like that's going to be 217. And then I add 6 again, so that's 36. 91 plus 36 would be 127. Add 127 plus 217. That is 344. So again, I will add 6. Give me 42. 127 plus 42 is 169. 169 plus the 344 is going to be 513. Now, when you look at this row of numbers, they may not look significant either. However, like the row above, they are going to be a special group. The common row of differences is in the third row, so I'll give you a hint and tell you that it's going to be n cubed. In fact, it's going to be n cubed plus 1. All of these numbers are 1 greater than a perfect cube. 1 to the third plus 1, 2 to the third plus 1, 3 to the third plus 1, and so forth. Next example is our first geometry pattern. So look at these shapes, pause, and can you draw the fifth one? I'm going to assume you've paused and ready to move on. What I'm trying to draw here is a 7-sided shape, 1, 2, 3, 4, 5, 6, 7, that looks like all the sides are equal. It looks like all the angles are equal. And I noticed that in any of the polygons that have an odd number of shapes, there's a dot right in the middle. A conjecture is a prediction based off of inductive reasoning. So when you were looking at those number examples before, you were making a conjecture up to what was going to happen next. And generally, we write a conjecture as a conditional statement. A conditional statement is a statement that contains a hypothesis if P is some phrase, and a conclusion, then Q, and again, Q is some phrase. So let's look at an example of that. Instructions say to make a conjecture using the following examples. Well, I do 3 plus 5 is 8, 7 plus 11 is 18, 13 plus 1 is 14, 9 plus 3 is 12, 37 plus 5 is 42, and 121 plus 21 is 142. What do I notice that all 6 of these problems have in common? Well, what I'm noticing is that if you add 2 odd integers, the result is an even integer. So there is my conjecture, and it's phrased as a conditional statement. I like that. Now, just because I made the conjecture, that doesn't necessarily mean it's true. And maybe this conjecture is true, maybe it's false. The thing about inductive reasoning is it's a good way to find a pattern, and I want to make some sort of conjecture about it. It's a good way to get the mathematical process started, but again, it's not proving it definitively. Let's look at an example. I have noticed that students with the last name A through L have been in my classroom every Wednesday since August 31st. So it says use inductive reasoning to make a conclusion. So I'm going to say, if today is a Wednesday, then, for typing skills, and students with the last name A through L must be in my classroom. Again, I think that's true based off of what I've seen before. So I'm saying this is always going to be true. Based off of what I've seen, I believe that every Wednesday, if it's Wednesday, then students with A through L will be in my classroom. Is this true or false? So think about that. If today is a Wednesday, is a guarantee that there will be students in my classroom with last names A through L. Trying to poke holes in the argument, and we're looking for what's called a counterexample. A counterexample is a way to prove that a conjecture is false. And a counterexample, you want to find a situation where hypothesis is true, but conclusion is false. That is what a counterexample is. It proves that a conditional statement is true by finding a condition where the hypothesis was true, but the conclusion was false. So I'm not looking at this and saying, well, I had students with the last name M through Z in my classroom, and it wasn't Wednesday. That would not be a valid counterexample. I'm not trying to make the back part work. I'm trying to, or even not work at the beginning. I want to find an example where it is a Wednesday, but students with A through L were not in my classroom. If I look at the schedule going forward, I'll see that on September 23rd, there is no school for freshmen, sophomores, and juniors. There's another day in October where that's true as well. So here's my counterexample. September 23rd is a Wednesday, so it's true for this part, but it's false. There are not students A through L in my classroom. Deductive reasoning using facts and logic. This is the way that we prove something is definitively true in mathematics. Not just that we see a pattern, but we can prove using facts and logic that it's true. Let's go to the example that we were just talking about before. I noticed that 3 plus 5 is 8, 7 plus 11 is 18, 13 plus 1 is 14, and maybe some other examples. After noticing all that, I make a conjecture based off of the pattern that I see. I say that if you add 2 odd integers, then the sum is an even integer. I've come to this conclusion using inductive reasoning. So can I find a counterexample? So I'm looking for a situation where I'm adding 2 odd integers and I don't get an even integer. I could try a bunch of examples. If I find even one that doesn't work, then I know my conjecture is false. However, I can't find one for this. So I believe that my conjecture is true. So I'm going to try to prove it using deductive reasoning. If you can follow my logic here. If n is an integer, then 2n must be an even integer. That's what it means to be even. And if I took any even integer divided by 2, the result is going to be an integer. So now if 2n is an even integer, then the very next number, the very next integer would be 2n plus 1, which would have to be odd. And if 2n plus 1 is odd, then if I add 2 more onto it, I skip over the even, get to the next odd number also. So 2n plus 3 would have to be odd as well. Now when I add these two odd integers together, I get 4n plus 4. And I want to check to see, is 4n plus 4 even? So 4n plus 4 divided by 2 gives us 2n plus 2. I'm not getting any kind of a fraction. 2n is definitely going to be an integer if n itself was an integer. And if I add 2 more onto it, it's still going to be an integer. So I just proved that, yes, if you add two odd integers together, the result is going to be even. Could we have said more with this conjecture? For instance, could we have made this into a biconditional? A biconditional is when we use the phrase if and only if, or abbreviated to IFF. With this example, it would have been, go and scroll down. The sum of two integers is even if and only if you add two odd integers. So what I mean by that is, just like we had before, if you add two odds and the result is even, but it's also saying the converse of that. If we switch it, it's saying also that if your sum is even, then you must have added two odd integers to get there. It's saying both of those. So do I think that this biconditional is true? Well, again, I already proved this first part. Is the second part true? If I have an odd or an even answer, did I get there by adding two odd integers? So if I can find a counterexample where I have a result that's even, so two numbers, let's say, that add up to 14, but the two numbers that got me there weren't odd integers, maybe like 6 plus 8, then I just disproved this biconditional. I found a counterexample. I found a counterexample where the hypothesis worked, but the conclusion didn't. It's not very often where you can use a biconditional. In fact, generally the only time we use biconditionals is for definitions. An example where I might use it would be for the definition of perpendicular. For example, two lines are perpendicular if and only if the lines intersect at a right angle. In other words, what I'm saying here is two things. If two lines are perpendicular, then their intersection is a right angle. Simultaneously, I'm also saying it, if two lines form a right angle with each other, then those two lines must have been perpendicular. A lot of times we like to write our definitions of biconditionals because they make them more specific. So can I write out my earlier conjecture as a true biconditional? We just looked into that and said, no, we couldn't do that because it didn't work both ways. Process of mathematics. You use inductive reasoning to identify a pattern. Based off of that pattern, you make a conjecture, generally in the form of a conditional statement. If this, then that. You test your conjecture to see if you can find any counterexamples where the hypothesis was true and the conclusion wasn't true. And if you find a counterexample, that means that your conditional statement and conjecture were wrong. But if you can't find any counterexamples, then try to prove your conjecture using the deductive reasoning, using proof, using facts and logic. And if your conditional statement works, does it work as a biconditional? But generally, those biconditionals only work for definitions. So we don't want to overstep our bounds and always try to go to the biconditional.